Let me start with a simple question. Why do most AI projects in manufacturing fail? It's not because the technology doesn't work, it's because they never solve a real problem. And that's especially true in metal additive manufacturing. Because if you look at what's happening on the shop floor today, you're generating huge amounts of data. Acoustic signals, melt pool images, machine logs, terabytes per build. But very little of that is actually driving decisions. Most teams get stuck in what I'd call pilot purgatory, running experiments, testing algorithms, but never creating real impact. And the reason is simple. They start with the technology instead of starting with the problem. So instead of asking, what can we do with AI? The better question is, what's currently costing us money and can data help us fix it? Because that's where AI actually starts to make sense. Once you've identified a real problem, the next step is to ground it in business value. Before you build anything, you need to understand where are the losses, scrap, rework, downtime, and more importantly, how much are they costing you? Because if you can't quantify the problem, you can't justify the solution. Then you flip it. What would it cost to solve this with AI? If the answer doesn't clearly outweigh the benefit, you stop there. And that's not failure, that's avoiding wasted effort. Now, assuming the numbers do make sense, the next question is this even the right type of problem for AI? Because not every problem is. If something can be solved with a simple rule, like shutting down a laser when oxygen exceeds a threshold, you don't need AI. That's a deterministic problem. But a lot of what happens in metal AM isn't that clean. You're dealing with complex interactions, thermal behavior, material response, process variation, and in those cases, there's no clear rule. That's where AI becomes useful. Not because it gives you certainty, but because it gives you probability. Instead of a hard yes or no, you get insight like, there's an 87% chance this build will develop a defect. And that's what allows you to make better decisions under uncertainty. At that point, it helps to simplify things even further. Because most AI problems you'll encounter fall into just three categories. You're either trying to figure out, does something look normal or not? What value should I expect? Or what exactly am I looking at? And those map directly to three approaches. If you're spotting something unusual, that's anomaly detection. If you're predicting a number like tensile strength, that's regression. And if you're identifying or labeling something like a defect in an image, that's classification. It's simple once you see it that way, but getting that mapping wrong early on can cost you months. Now here's where things usually get difficult, because even if you've picked the right problem and the right approach, everything comes down to your data. And this is where most projects break down. Because raw data isn't enough. What you actually need is labeled data, clear examples of defects, outcomes and events that the model can learn from. And producing that requires expert input, engineers, metallurgists, domain knowledge, which makes it slow and expensive. So before you go any further, you need to be honest about one thing. Is your data actually ready for this? It also helps to understand what kind of data you're working with, because not all data behaves the same. Sometimes you're dealing with structured data, tables, logs, parameters. Sometimes it's time-based signals, sensor data changing over time. And sometimes it's unstructured, images, video, complex visual data. And each of those requires a different level of modeling complexity. So the goal isn't to use the most advanced AI possible. It's to match the simplest effective approach to the data you have, which leads to another common mistake. A lot of teams assume they need to build everything from scratch, custom models, custom pipelines, full AI infrastructure. But in reality, that should be your last option, because in many cases, you can get most of the value using what already exists. Pre-trained models, existing tools, or transfer learning. So instead of asking, what can we build? It's often better to ask, what can we reuse? And finally, there's one more constraint that's easy to overlook, but critical. Trust. Because if your model makes a prediction, but no one understands why, they won't use it. And in regulated industries like aerospace or medical manufacturing, that's not just a preference, it's a requirement. So there's always a trade-off. More complex models can give you higher performance, but less transparency. Simpler models may be slightly less accurate, but much easier to explain. And in many cases, explainability wins, because a model that isn't trusted isn't used. So when you step back and look at all of this, the path forward is actually pretty clear. AI in metal additive manufacturing doesn't start with a massive transformation. It starts small. One clearly defined problem. One measurable outcome. One place where better decisions would create real value. And if you're not sure where to look, start with your engineers. Look at where they're relying on experience. Where they say, "I've seen this before." Because that's human pattern recognition. And that's exactly where AI fit. If this was useful, do subscribe, because in the next videos we'll break down real use cases in Metal AM that are already delivering results. Thanks for watching.